Okay, so welcome back to this video on limits in the LP space. Okay, so what we're going to do in this video is prove that if we have, get some intuition for why if we have a sequence of sequences in the LP space which converge termwise, that doesn't necessarily imply that they converge in the LP metric space. So let me draw a picture. So let's say we have some sequence S, which is a sequence of sequences, so x1, x2, x3, etc. And that's a sequence of sequences which are all in LP. So xi is an element of LP. So absolutely every single one of these sequences is within the metric space. So that means that it obeys, that each of these sequences obey the property that the sum of all the terms of them, so the modulus of all the terms, so let me just write this out, the sum of the modulus of all the terms, so the ith sequence we're looking at, remember this notation from the previous video, xi, the superscript now, denotes which sequence we're talking about, the j subscript denotes which term of that sequence we're looking at, j is equal to 1 to infinity to the modulus to the power of p, that is finite, basically. So all of the sequences in this sequence of sequences obey that property. So let me just draw a picture. So x1 is equal to some sequence, x1, 1, x1, 2, x1, 3. So the subscript again denotes the term of the sequence, of the first sequence which it represents, and the superscript denotes which sequence it belongs to. x2 is equal to x21, x22, x23, etc. And remember, all of these terms are real or complex numbers, depending on whether we're talking about real or complex LP spaces. Okay, and this sequence of sequences is going to converge pointwise. So this sequence converges pointwise. And what I mean by that is that if you look at all the termwise sequences, so if you look at the sequence of real or complex numbers, which is the sequence of all the first terms, basically, that converges, and let's say it converges to some, what should we denote it? We'll denote it x1 down here, okay? So we'll say that this converges to some limit x, basically. But of course this sequence of sequences might not converge to some limit in dp, but the sequence of sequences does have a pointwise limit, and what that means is that if you look at all these termwise sequences, every single one converges, basically. So if we look at this termwise sequence, which is the sequence of all the second terms, that's going to converge to some x2, let's say. Okay, and if we look at this next one, the sequence of all third terms, then that converges to some x3. Okay, right. So each one of these termwise sequences does converge as a sequence of real or complex numbers, and therefore we can construct this sequence, which is the pointwise or termwise limit of this sequence of sequences. However, it is not necessary that as far as the dp metric is concerned, that this sequence is in fact the limit of the limit of this sequence of sequences. But I want to stress one thing: if it is not the limit within this metric space, then this sequence of sequences has no limit. It's not convergent within that metric space, because as we proved in the previous video, if the sequence does converge in LP, then it implies that what it converges to is the pointwise limit, and all the termwise sequences do exist, and they do converge to some limit, and basically the limit sequence in the dp metric space is exactly the pointwise limit sequence here. However, if you have a sequence of sequences which converge pointwise, that is not a necessary. It's not a sufficient condition to converge in this LP metric space, although it is a necessary condition. So it's a necessary but not sufficient condition. So if we look at all the sequences in LP, which, see, if we look at all the sequence of sequences which converge in LP, then they are a subset of all the sequences in LP which have a pointwise limit. So this is the set of pointwise limits. This is the set of sequences which converge in DP. Okay. Right, so let me try and give you some good intuition for why this is the case. So if each one of these termwise sequences converges, what does that mean? That means that for all epsilon greater than 0, there exists some n which is an element of the natural numbers, such that if little n is greater than or equal to big N, then it implies that the distance between, let's pick an arbitrary sequence, so we'll say x little n I, so we pick the ith sequence, and its termwise limit is going to be less than epsilon. So pick whichever sequence you like, and I should probably put that at the start. For all I is an element of the natural numbers. So for all of the termwise, all of these termwise sequences, and for all epsilon you like, there exists some big N, and I should probably put that big N is now going to be a function of not just epsilon, but it's also going to depend on I, and that's the crucial bit, that you give me some epsilon, and I can find you some some big N for this orange sequence. So for this sequence of first terms, I can find you some x big N. So let's say x big N1, such that if you take any term in this sequence beyond that big N, it is going to be a distance away from this termwise limit x1, which of course in the real and complex numbers just means the modulus of the difference. So I'll just put that in, minus xi is less than epsilon. I can find you a point after which, if you take any term in this termwise sequence, it's within that within the epsilon distance of this termwise limit. I can do the same thing for this pink sequence, this sequence of second terms. The problem is that the n is not necessarily going to be the same thing. It might be, but it's not necessarily going to equal the same thing. So in fact, I should probably denote that by saying this n is a function of, in fact, I might subscript it. I might just subscript it I, basically. I won't denote that it's a function of epsilon, because that's normal, but it being a function of I is important. So then again, we have some xn2 here, and for the second sequence there, so that should be a 1 there rather than I. Okay, and this is the point for the pink sequence, for this sequence of second terms, after which, if you take any term in that tail end and ask what's its distance from the termwise limit, then it will be less than epsilon. And again, you can continue, and you'll get some. I'll draw it on the picture. You'll get some x big N free, such that if you take any term in the green sequence beyond there, it will be within epsilon of the termwise limit. The problem is that these ni's are not necessarily bounded as a set, i.e. it might not be possible to find some big N which is greater than absolutely all of them, i.e. greater than n1, greater than n2, greater than n3, etc. basically. It's not necessarily going to be possible to do that. Right. Okay, so let's look at what we want to try and do. We want to try and prove that this doesn't necessarily imply that this sequence of sequences converges to this sequence that we get from this sequence we have of the termwise limits. So if we wanted to prove that, so let's try and prove that this does converge to this and see what problems we get. Okay, so if we wanted to prove that this does converge to this, then what we would need to prove is that whatever epsilon you give me, so for all epsilon greater than 0, I would be able to find some, let's say, big M, which is an element of the natural numbers, such that if little m is greater than or equal to big M, it would imply that the distance between the x little mth sequence and this sequence x, this limit sequence here, this sequence of termwise limits, needs to be less than epsilon. I need to find you something like this, some sequence x some sequence x big M, such that if I take a sequence x little m, the distance between that sequence x little m and x is going to be less than epsilon if this x little m is in the tail end, i.e. it's after this x big M. Okay, so now let's just write out what the definition of this distance is. Well, it's it's the sum from I is equal to 1 to infinity of the modulus of x. Now, where do you put that? The xmi minus xi to the power of p, all of that to the power of 1 over p, needs to be less than epsilon, okay? Right, we need another piece of paper then. Let's do it on the back of this. Right, so what we need to prove this if we wanted to show that this sequence of sequences does indeed converge to this sequence of term-wise limits. So just to recap what this distance is, if we write out what the sequence x little m is, it's x little m1, then we've got x little m2, x little m3, x little m4, and I'm sorry it's going off on a bit of a hill there, x little m5, x little m6, etc. And basically what we are doing is we're saying take this first term here in the nth sequence, subtract off the first term in the term-wise limit sequence, take the modulus of that, raise it to the power of p, and then add it to the same thing for the second terms, the same thing for the third terms, etc. onwards. Add them all up and do that to the power of 1 over p. That needs to be less than epsilon. Right. Okay, so that's a difficult thing to request. What we know is that we can make because each of the term-wise sequences does converge to this limit, I can certainly find you a point after which it's smaller than whatever epsilon you want, but that doesn't imply that they're all going to sum up to something like this. Okay, so what we could attempt to do, firstly, just rewriting this distance function here, what we get is that the sum from I is equal to 1 to infinity of the modulus of xi m minus xi to the power of p needs to be less than epsilon over p. So that makes it slightly easier. So what we could attempt to do, I'm going to give you a demonstration, a nice demonstration of why this is difficult. So what we could attempt to do to try and make this series less than epsilon over p is we could attempt to say that we want xmi minus xir p, and again I think I've made the mistake. Let's make this dummy variable r again. I did this in the previous video. Use the I, and we're using the I as a specific example, so let's make that a dummy variable r, because it doesn't matter, we're just summing over r basically. So let's say we want to make the rth term of this series, so what have I done there? xr to the power of p, like that. Let's say I want to make the rth term of this series, which remember I'm adding up all of these for r is equal to 1 to infinity. So let's say I take the rth term of this series, and if I make that less than epsilon over p to the power of 2 over r, if I did that, then would this be true basically? It would, and let me show you why. Because what I would be summing up from r is equal to 1 to infinity, if I wanted to sum this series up, xm to xr minus xr to the power of p, then that is going to be less than now, strictly less than, the sum from r is equal to 1 to infinity. And again, I'm doing this for all r, so for all r is equal to 1, 2, 3, etc. So for the first term, what you do is you say, okay, I want to make the modulus of xm r minus xr to the power of p. I want to make that less than epsilon to the power of p over 2 to the power of, well, my r is 1. So I'll substitute in 1 there, and I'll get over 2. And I can do that because of the fact that all of these term-wise sequences are converging. So I can certainly find you a point after which that is true. Similarly, I can do that for all of these terms. I can find points, basically. I can find points in each of these. I can find points, n1s if you like, for which if you take any point in the sequence after that, this statement is true, basically. But again, the problem is that these ni's aren't necessarily, m1, n2, m3s, etc., aren't necessarily going to be equal to one another. So then what this, if I could do that though, what this series would be equal, less than, would be epsilon to the power of p over 2r. Now epsilon to the power of p is just some constant, so we can pull that out, and then we get the sum from r is equal to 1 to infinity of 1 over 2r. Now, let me just write out what that is. That is equal to epsilon to the power of p of 1/2 plus 1/4 plus 1/8, and hopefully you can see already what that is going to converge onto. I mean, you should have seen the geometric series before. If you're studying functional analysis, I'm sorry for patronising you. Okay, so this is equal to 1, basically. This converges to 1. So that implies that this sum would be less than epsilon over p, which is exactly what we want, basically, if we can make this true. So if we can make this true, if I could find some little m for which this is true for all r is equal an element of the natural numbers, then I'd be in business, basically. What I'm going to show you is how difficult, that you can't necessarily construct an m like that. Okay, so what we need is to find some big M, basically, for which this is true. For all r is an element of the natural numbers, i.e. what we need is an x big M, so let me bring this down. What we need, and let me bring this up here, what we need is an x big M, some point in this sequence of sequences, such that if you take any sequence beyond that x big M, that this statement here is true, i.e. the distance between the first term and the first term of the nth sequence and the first term of the termwise limit sequence is going to, the modulus of that to the power, the modulus of the difference between them to the power of p is going to be less than epsilon to the power of p over 2, in this case r is equal to 1, so you'd say over 2. Okay, then you'd go along to the second terms and you'd say, okay, now if I do the same thing for the second terms, I take the second term of the nth sequence and subtract off the second term of the termwise limit sequence, take the modulus of that and do it to the power of p. That needs to be less than epsilon to the power of p over 2, but now we're talking about the second term, so that should be over 2 to the power of 2, etc. So you need that to be true. Of course, you could try and find a different way. You could try and find a different way to make this series convergent. This is just an example of how you could try and do it. Basically, whatever clever ploy you come up with to try and make this series converge to something, you're always going to get a requirement like this, which is going to require all of these termwise limits to obey some condition, and of course they're all going to obey it at some point. So some n1, some n2, some n3s, but the n1, n2, n3s might not be bounded, so it might not be possible to find a big M such that all of them are obeying it at the same time. So let me put that into writing, hopefully. Right, okay, so we need a big M, which is an element of the natural numbers, such that if little m is greater than or equal to big M, then it implies that the modulus of xmr minus xr to the power of p is going to be less than epsilon to the power of p over 2r, and that needs to be true for all r is an element of the natural numbers. I need a big M such that that holds. So let me draw out the picture again, because I can't be bothered with continuously switching back and forwards between it. Okay, so if I draw the picture again, we have we have our sequence of sequences. So we have x1, x2, and these are both sequences. So here's x1, 1, x1, 2, etc. Here's our second sequence. So x1, 2. Oh dear, no, what have I done? x2, 1. That should have been x2, 2, etc. And then it goes down, and we need some x big M here, which is x big M1, x big M2, x big M3, etc. Such that if you take any sequence beyond there, so x little m, which is x little m1, x little m2, x little m3, such that if you take any sequence beyond there, the distance between, I've converted the distance into another requirement, that this statement here is true for this sequence here. So let's put the termwise sequence down here. So this is the sequence of termwise limits, x1, x2, x3. So that's the, if you take the limit of all the sequence of first terms, you get x1, the limit of the sequence of second terms, you get x2, etc. Okay, so what we need to be true is that whatever term of these sequences you choose to compare, if you look at the first terms, then if you compute this for the first terms, i.e. you take the first term, you let r equal 1 basically, and you take the distance, the difference between the nth, the first term of the nth sequence and the first term of the termwise limit sequence, and take the modulus of that and do it to the power of p, it's going to be less than epsilon to the power of p over 2, and you fill in r is equal to 1. So that needs to be true. Then we need to go along to the second term and check that it holds true there. So you substitute in r is equal to 2 and it needs to hold for that, and you need to do it again for r is equal to 3 and it needs to hold for all r as an element of the natural numbers. So you need to go along every single one of these and check that basically you need to be able to find some big M is an element of the natural numbers, such that if I take any sequence x little m beyond that beyond or equal to that x big M, so beyond or equal to here, then this basically needs to hold. That is a steep requirement. It's not the only way you could make this distance function converge in that way, but it's an example, and I'm showing you how difficult it is to actually get it to work. And basically, if you come up with any other clever ploy for making this distance less than epsilon, then you're going to have some similar requirement to this. So let's discuss what we can do. Because each of these termwise sequences does indeed converge, what we can do is say that for all, we can say for you give me an I. So let I be an element of the natural numbers. So pick a termwise sequence to examine. So we're looking at all the ith terms basically, and the ith termwise limit basically. Okay, so let I be an element of the natural numbers. Because the sequence of ith terms does indeed converge to its termwise limit, which is xi down here, okay? So let me just draw some of these out. So what have I done here? Why is that bracket there? So x1i, the ith term of the first sequence, then we have x2i, the ith term of the second sequence, this is x big mi, this is x little mi, so the ith term of the little mth sequence. Because this termwise sequence does indeed converge to xi down there, then it's possible that I can find there exists some, let's say, n big I, which is an element of the natural numbers, such that if little n is greater than or equal to n big I, then it implies that the modulus of the ith term of this termwise sequence, x ni minus the modulus of the difference between the ith term of this termwise sequence and the termwise limit of this ith termwise sequence, okay, to the power of p is going to be less than epsilon over p to the power of 2i. Okay, and the reason for that is that if I just if I do both sides to the power of 1 over p, then I get the modulus of xni minus xi should be less than epsilon, and then so I've done both sides to the power of 1 over p, and then I need 2 to the I over p, basically, like that. Okay, basically, because this termwise sequence converges, I can always find you some point in this sequence. So I'll say down here, let's say, in fact, I should put it above, of course. I should put it above. So let's put it up here. Some x ni I down there. So I can find some point in this termwise sequence such that this is certainly true, because this is just some number greater than 0. So I can certainly find a point in the sequence where from that point onwards, the distance between any term and the limit of that sequence is going to be less than that, and that it will imply that that statement above is true. So basically, I can make this statement here true term by term. So I can go through and come up with an ni for every single term-wise sequence. So if I imagine doing it for another sequence here, which I won't draw, but some other sequence, I can find you some other points. So let's say some x big N I minus 1 of the sequence of I minus 1 terms, where this statement will be true again, where you substitute obviously in the relevant I here. Okay, so I can come up with these NIs basically, so I can produce this set N1, N2, N3, etc., which are these natural numbers, these points in these term-wise sequences, after which this statement is going to be true, and after which I have a hope of achieving this. The problem is they might not necessarily be bounded. This set N1, N2, N3, they could be, 1,000, 1 billion, 300 billion, they could go off and off and off. All this says is that there will exist some natural number. It doesn't tell you that it's going to be small, so this could go off, and it might not be possible to find some big M which is bigger than all of them, because that's what you want. If you want this to be true for absolutely all of the natural numbers, i.e. for all of the term-wise sequences, then you need to make big M greater than all of these, because these are the points at which it becomes true for each of the terms. So after Ni, so after this point, this statement is true. This statement is true for R is equal to I. Okay? For N1, this statement is true for R is equal to 1, from N1 onwards. From N2 onwards, this statement is true for R is equal to 2, but it's not necessary that we can find a big M which is going to be bigger than all of the NIs, because they might be unbounded, and it's not a finite set, basically. So that is why it is not necessarily true that if you have a sequence of sequences which converges pointwise, so all of the term-wise limits exist, it is not necessary that the limit of that sequence exists in the metric space LP. However, if it does exist, then it will most definitely converge to that term-wise sequence, is what we have discussed in these videos on limits in the LP space. And of course, just to finalize this, this statement here, that the distance between the two had to be less than epsilon, which I converted into this by just taking 1 over p on both sides. I did not have to achieve that via this. This was a way of achieving that. So going from that to that was a choice. This was a choice, and it wasn't one that I had to make. There are loads of other ways you could try and do this, but basically every single way you try and come up with, you are going to get some similar condition to this that you need to find a point after which it holds for all of the term-wise sequences, and basically you'll be able to find points where for each of the term-wise sequences it holds, but they won't necessarily be bounded, i.e. you won't necessarily be able to find a point after which it works for all of the term-wise sequences, because you've got an infinite set of numbers after which it works, and that's not necessarily bounded above.